Hello everyone, welcome to learn the course of basic principles of steel structures. In this chapter, we will put our focus on the following points. Firstly, the types of axially loaded members. Secondly, strength and stiffness of axially loaded members. Third, global buckling and local buckling of axially loaded members. Fourth, design procedure of axially loaded members. In this lesson, we will start with the first 2 points, that is, to study the types, strength, and stiffness of axially loaded members. First of all, let's see what an axially loaded member is. A structural member that is subject to forces along its axis is called an axially loaded member. According to the direction of the force, the axially loaded member can be divided into 2 categories: axially loaded tension member and axially loaded compression member. Axially loaded members are widely used in practical engineering. For example, the members in a plane truss, space truss, and tower truss can be treated as an axially loaded member. Further, struts in the working platform are also an example of an axially loaded member. According to the cross-section form, the axially loaded member can be divided into 2 categories: the solid web member and the built-up member. The common cross-section of a solid web member includes the round section, pipe section, angle, T-shaped, I-shaped, H-shaped sections, and the channel steel, etc., as shown in the figure 1. Built-up members are generally made up of 2 or more individual sections, such as angles, channels, or S-sections, as shown in figure 2. The individual sections are properly connected along their lengths by lacing bars or button planes so that they act together as a single unit. Lacing bar and button planes together are called the lacing system, as shown in figure 3 and figure 4. In structure design, the requirements for axially loaded tension members and axially loaded compression members are different. For an axially loaded tension member, the strength and stiffness of the member are required to be verified. However, the axially loaded compression member needs the requirements mentioned above. Besides, the stability of the member needs to be verified in the design as well. Next, let's study the design methods for the strength of an axially loaded member. The ultimate strength of an axially loaded member can be determined based on the member's ultimate limit state. This ultimate limit state can be defined as the state where the average stress acting on the cross-section of the members reaches the material yield stress. When the axially loaded member has no holes in it, we can use equation 1 to determine the cross-section yielding strength of the axially loaded member. In equation 1, N is the design value of axially loaded tension or compression force, and A is the gross section area of the member. F is the design value of tensile or compressive strength of the steel. Further, when the designed axially loaded member has holes in it, which reduce the cross-section, the stress on the cross-section will be no longer uniform under tension or compression load. Holes in the members will cause stress concentration at surface loads. The point adjacent to the hole reaches the yield stress first. Then, on further loading, the stress at that point remains constant at yield stress, and each fiber away from the hole progressively reaches the yield stress. Deformations continue with increasing load until finally the rupture of the member occurs when the entire net gross section of the member reaches the ultimate stress Fu. The design strength of axially loaded members due to night section rupture is given in equation 2. Next, let's study the contents of the stiffness of the axially loaded members. In order to ensure the normal serviceable function, a minimum stiffness is stipulated for an axially loaded member to prevent undesirable lateral movement or excessive vibration. Their slenderness ratio usually characterizes the stiffness of axially loaded tension or compression members. Thus, the stiffness can be ensured by limiting the maximum slenderness ratio of the member not exceeding a certain value, say equation 3. In equation 3, L0 is the calculated length of the member, and I is the radius of gyration. Lambda with a square bracket is the allowable slenderness ratio of the member. The allowable slenderness ratios of tension members and compression members are given the code design of steel structures. In this lesson, we have studied the strength and stiffness of axially loaded members. In the next lesson, we will learn the global buckling of axially loaded compression members. See you next time.